This is part 11 of lecture 11 of ELEC5300. We're going to look at some properties of the solution of the deterministic least squares problem that we presented earlier. Now remember that the estimator, or the output of the estimator that we get, this x hat ls, is actually going to be a random variable because it depends on y, right, where y had some random components due to the noise. Right? So even though x is not random, the thing that we're trying to estimate it with is random because of that noise. And so one of the questions you might ask is, well, if this is a random variable, what is the mean or the average value of this random variable? And you hope that that's equal to x, right? In that case, the estimator is unbiased. So we can prove that that's the case just by putting in the form of the solution that we derived earlier, and then we replace y by its definition, and then we can expand this out. So when we do that, we get an HTH inverse times HTHX, right? And then an HTH inverse times HTV. Now, this and this cancel each other, so I just get x, and this you can see is just B0, B. And if I take the expected value of this, then I just get x plus the expected value of this, but the expected value of this is 0 by our zero mean assumption. So therefore, we show that the estimator is unbiased. In addition to using zero mean, we'd also like to show that the estimator x hat ls is actually close on average to the mean. In other words, if we're going to measure the distance, we're going to measure it with the variance. We want to show that that variance is as small as possible. And for this part, I'm going to have to introduce a new assumption on the noise. We already assumed that the noise was zero mean. Now we're going to add this new assumption here, which is that it is uncorrelated. And all of the components have the same variance, sigma squared. So this is kind of like a white noise assumption on the noise. So the covariance matrix of the noise is just sigma squared times the identity matrix. Now, when we say that this has minimum variance, remember this has multiple components, right? And so when we say that it's minimum variance, we mean that, well, if we have any other estimator, right, this would be some other matrix B, right, which would take y into x, and assume that it's also unbiased, right? So it's some other unbiased estimator. Then x here has multiple components, right? It has n dimensionals here. So what we'd like to show then is that each one of those components has the smallest variance, right? And so here, if I take this one, this is really a covariance matrix, right? So it is something like this. Then let's say x was two-dimensional. Then the diagonal terms would be like the variance of the first term, right? So x hat 1 minus x 1 quantity squared. So it would be the expected value of this thing. And then the other one would be expected value of x2 hat. And so what you want to show is that these two are small for the optimal solution. In other words, that if I had any other linear estimator, b hat y, that the diagonal here would be larger than the diagonal element of the optimal estimator, the corresponding diagonal element here. To prove the minimum variance property, we're just going to take any other estimator. Now I'm going to substitute in the function for y here, and then I'm going to expand it out like this. And because this is unbiased, it must be true that when I take the expected value of this, I get x. And so since this is zero mean here, when I take the expected value of this, I get just bhx. And so in order for this to be x, I must have that bh is equal to the identity matrix. So x hat then is just x plus bv, and so the only thing that's happening is that bv is just kind of shaping the noise, right, in a different way. And so then now you see, well, we assume that the noise had all equal components, so it would seem like that what you'd want to do is somehow treat each component of the estimate the same. So the covariance matrix then, Kx hat, is given by this thing here, right? And now if I say, well, x hat minus x is just bv, then this is just bv squared, or bv times v transpose b transpose. I can take the b's outside, and I get this. And remember, this covariance matrix here, by our assumption previously, is the identity matrix times sigma squared. So I just get sigma squared b times b transpose. Now, in particular, if I have the optimal LS, right, then this is still true because this was true for any b, right? So if I choose the optimal b, it's also going to be true. But I know what the solution for the optimal b is, so I can substitute that formula into here, and you can see that I can do cancellation between this one and this one. So I get sigma squared h transpose h inverse. Now, I really am interested in the difference between the covariance matrix for the optimal case and the non-optimal case. So I'm looking at now the difference between b minus b0, and I'm taking b minus b0 times b minus b0 transpose. And so then this one is going to give me, by expansion, this thing here. Right? And I can substitute in the form of B0 or B0 transpose into here. So for example, if I have B times B0 transpose, I know the form of B0 transpose is given by this. I know that BH, right, is the identity matrix. Right? So I just get this. And so therefore, I get that this term, and this term are all the same. And so I can cancel, let's say, this term here and this term here. And so therefore, I get this equation right here with what's left over. Right? And now this is the covariance matrix scaled by 1 over sigma squared of the non-optimal estimate. This is the covariance matrix of the optimal estimate scaled by 1 over sigma squared, as we can see here. And I know that these guys are have the same diagonal as the elements of these guys, right? But because this is a square term here, the diagonal elements of this thing here are always going to be greater than or equal to 0. So I know that the diagonal elements of this are always going to be smaller than the diagonal elements of that. And that concludes the proof.